Now we get to the second part of Chapter 5, the binomial distribution. There are 4 characteristics of a binomial experiment where you're able to use the binomial formula to calculate probabilities. Your trials have to be identical. We use a lowercase n to represent the number of trials. Each trial has 2 possible outcomes. One of them is referred to as a success and the other one's the failure. Now the probability of a success has to be the same no matter which trial it is. And that's due to the fact that the trials have to be independent. The outcome of one trial doesn't depend on the outcome of another trial. Now what the binomial formula allows you to do is to find the probability of so many successes in the n trials. Now we're going to use the symbol x to represent the number of successes. So x is going to have to be less than or equal to n. Ordinarily, the smallest value that x can assume is 0. Now this is the formula for the binomial probability. N factorial, where n is the number of trials, divided by x factorial times n minus x factorial. P raised to the x power, p is the probability of a success and it's not going to change. The exponent is x, that's how many successes you want. 1 minus p is going to be the probability of failure because there are only 2 possible outcomes and you want the rest of them to be failures. So the rest of them is going to be n minus x. So n minus x is the exponent on 1 minus p. X is the exponent on p. The n factorial divided by x factorial times n minus x factorial calculates the number of possible arrangements of the successes and the failures in the n trials. Now remember, 0 factorial by definition is equal to 1. Let me use 3 as an example. 3 factorial would be 3 times 2 times 1, which would be 6. Now the n factorial divided by x factorial times n minus x factorial gives you the number of possible arrangements of the x successes in the n trials. The p raised to the x times the 1 minus p raised to the n minus x is going to be the probability of a particular arrangement. The Evans electronics example is going to be used to show how the formula works. Now they're concerned about their low retention rate, and they've been seeing a turnover of about 10% of their hourly employees. So they're going to choose 3 of their hourly employees. That's the number of trials. Think of it as a sample size. What's the probability that one of them is going to leave the company this year? Now the probability that any particular one leaves the company is 0.1 or 10%. So that's what the P is in the formula. N is the number of trials, and that's what the 3 is. But we want the probability that the number of successes, we're going to say that success is somebody that leaves the company, that the number of successes is equal to 1. Now first we're going to look at this from basic principles. We're randomly selecting 3 employees. So we have the first one, the second one, and the third one. We want the probability that one of them leaves. Well, that might be the first one. So the first case, the top row, is that the first employee leaves and the other 2 stay. But that's not the only arrangement. It could be that the second employee is the one that leaves. Now that's an or situation. Or it could be that the third employee is the one that's going to leave. Now when you look at a particular arrangement, the first employee leaves, and the second employee stays, and the third employee stays. What's the probability of that particular arrangement? Every one of these arrangements is going to have the same probability because we're looking at statistical independence. The fact that the first one leaves doesn't change the probability of the second one staying. Likewise, the probability that the third one stays is not affected by whether or not the first one leaves or not, or the second one leaves or not. The probability of staying is 1 minus 0.1, which is 0.9. Now this slide shows the calculations. The first arrangement, we're saying the first employee leaves, and the second one stays, and the third one stays. So that's going to be 0.1, that's the likelihood that the person's going to leave, times 0.9 times 0.9. So the probability for that particular arrangement is 0.081. But it's 0.1, one's going to leave, raised to the first power, times 0.9, the probability of failure, raised to the second power. The exponents have to add up to the number of trials. But that's not the only way. It could be it's the second employee that leaves. That's an OR situation. So you've got to add the probabilities together. You get 0.9, the first one stays, times 0.1, the second one leaves, times 0.9, the third one stays. It still turns out to be 0.081. It's just the 0.1 in this case is in the middle. But the product is still 0.1 raised to the first power times 0.9 raised to the second power. Or it could be that the third one leaves. So you get another 0.081. Now when you add all three of those probabilities together, you get 0.243. So the probability that one of the three employees is going to leave is 0.243. But that's just doing it on basic principles. But there's a formula that lets you mechanically go through and do these calculations. Now we're going to set it up as the successes and the failures. Leaving is a success. So the S, F, F, there's the first one is a success, the first one leaves, and the other two stay. So the other two are failures. So we got the probability of success times the probability of failure times the probability of failure. And you get the 0.081. This is assuming that the first one leaves. Now this slide shows all three possible arrangements. The first one leaves, the second one leaves, the third one leaves. But you get the probability of success times the probability of failure twice in each case. It's always 0.1 raised to the first power times 0.9 raised to the second power. And then when you add all three of them up, you get the 0.243 for the solution. So P is equal to 0.1, the probability that an employee is going to leave. N is equal to 3. There are 3 employees, there are 3 trials, and we want the probability that one of them leaves. So we want one success in the 3 trials. And you just plug in the numbers. N factorial is going to be 3 factorial. That's 6. Divided by x factorial, well, x is just 1, so that's 1 factorial, which is 1. N minus x factorial, well, 3 minus 1 is 2. 2 factorial is 2. So you have 3 factorial, which is 6, divided by 2, which is 3. And that's the number of possible arrangements. But that's what the factorial part does for you. Each one of those arrangements, we're going to have one success. So we're going to have 0.1 raised to the first power, which means we have to have 2 failures because there's 3 in all. So we're going to have 0.9 raised to the second power. And when you multiply 3 times 0.1 to the first power times 0.9 to the second power, you get 0.243 with the formula. Now this is another way that you can look at the problem in a visual sense. It's called a tree diagram. When you look at the first employee is either going to leave or is going to stay. Now regardless of which one happens, you get to the second employee and they're either going to leave or they're going to stay. But you're going to have a 0.1 probability for leaving and a 0.9 probability for staying. On each one of those paths for the second one, you get to the third employee. They're either going to leave or they're going to stay. So the ones that are marked in green out at the end is the end of the path where there's going to be one that leaves. So the first one that's circled, the first employee leaves and the second one stays and the third one stays. The second one that's circled is the first employee stays and the second one is the one that leaves and the third one stays. And the third one that's circled is a case where the first employee stays and the second employee stays and the third employee is the one that leaves. But you get the probabilities for all three of those cases and add them up and you've got the solution. Now Excel has a binomial distribution built into it. The function is binom dot dist. The first argument of the function is the number of successes that you desire. The second argument of the function is the number of trials. The third argument of the function is the probability of success. Then the last argument tells Excel whether you want the cumulative function or whether you just want the exact function. The cumulative function, if you put true, it'll add the probabilities up for you. But in this case, we just want to know what the individual probabilities are. So we're just going to use the exact version where that cumulative argument is false. Now you can see here that the formulas are being used. A5 is the first value of X. Now the dollar sign fixes the reference where it's always going to be A1. So we're always going to have three trials. A2 has the dollar signs on it, so that's going to be fixed. It's always going to use the 0.1 as the probability of success. But you can type in that formula that's in B5 and then just copy it and paste it into the other three cells, and it's going to work for you because the relative ones, A6, A7, A8, they're automatically going to be generated when you do the paste operation. Now this slide shows the functions when they've been evaluated and the numbers that you come up with for those functions. The probability of 0 successes would be the 0.729. Probability for one success, that one of the three employees leaves, is 0.243. The probability that two of them are going to leave is 0.027. The probability that all three of them leave is 0.001, which you could do that from basic principles by just taking 0.1 times 0.1 times 0.1. Now if you want the cumulative probabilities, just change the false argument at the end of it to true. A trick that you can use in Excel is rather than type out the word true, type out the word false. You can use 1 for true and you can use 0 for false. And a lot of times you'll see them used that way in functions. And this slide shows the values for the cumulative function. The probability that the value of the variable is less than or equal to 0 is 0.729, which is the same probability of equaling 0. The probability that the value of the variable is less than or equal to 1, you take what the value is for 1 and you add it to the value for 0. So 0.729 is what it was for 0. 0.243 is what it was for 1. So when you add 0.243 to 0.729, that's where the 0.972 comes from. I think the one for 2 was 0.027. So when you add that on, you get the 0.999. The one for 3 was 0.001. When you add it on, well, now you get up to 1. Because they've all got to be less than or equal to 3, because there were just 3 employees. Now, it used to be that all your textbooks would come with a binomial table in it, so that people wouldn't have to sit there and calculate those factorials to come up with those probabilities. And you'll still see a lot of textbooks that have those tables in them. But calculators have functions built into them. Things like Excel have these things built into them. So you really don't have much of a need to keep one of those binomial tables. But just to give you an idea of what those tables look like, we have the probabilities that go across the top, and we find p is equal to 0.1. And then for the case where there are 3 trials, we have x is 0 success, we have x is 1 success. And we come over to the column where p is equal to 0.1, and you can see the 0.2430. But the probabilities were pre-calculated and put into the table. Now, you remember mathematical expectation? To get the expected value of a discrete random variable, what you do is you multiply the value times the probability. But you have to do it over every case. Then add up all those products. The sum product function is a good way to do that in Excel. But if it's binomial, life is sweet. All you have to do to get the mean of a binomial is just multiply n times p. Take the number of trials and multiply it times the probability of success, and that will give you the mean every time. The variance, it's not quite as easy, but it's almost. All you have to do to get the variance is take n times p times 1 minus p. Now the variance, when you do it based on the definition, is kind of a bear of a calculation. You have to take the difference between the value of the variable and the mean and square it. But you have to do that for every possible value of the variable. But you come up with those squared deviations from the mean. Then all of those have to be multiplied element-wise against the probability values. And then you have to sum up all those products. But if you know it's binomial, all you have to do is take n times p times 1 minus p, and you've got the variance. And all you have to do to get the standard deviation is just take the square root of the variance. This slide shows the calculation of the values of the mean and the variance by making use of the sum product functions. In B10, the sum product function was used to multiply the x values times the probability values. The x values are in column A and the probability values are in column B. But the 0 times the 0.729, the 1 times the 0.243, and so on. When you add all those products together, you get the 0.3 that's down in B10. Then in column C, the difference or the deviation between the x value and the mean being 0.3, those differences squared were calculated. So for example, in row 5, you take the difference between 0 and the 0.3 and you get a negative 0.3, and you square it and you come up with a 0.09 that's in C5. Likewise, in row 6, you take the difference between the 1 and the mean. 1 minus 0.3 is 0.7, and you square that and you come up with the 0.49 that's in C6. But once you get the squares of the deviations from the mean, once you get those values squared, then you can element-wise multiply those numbers times the probabilities and sum them up. So I have the sum product function to do that down in C11. So when you take the 0.09 times the 0.729, you take the 0.49 times the 0.243, and so on. Add those up, you get the 0.27. Now, it took a while just for me to say all of that. It's much, much faster just to take n times p times 1 minus p to come up with that calculation. And finally, this slide just illustrates plugging the numbers into the formula to get the mean, to get the variance, and then take the square root, and you've got the standard deviation. In general, when you have a discrete probability distribution, it may take a while to figure out what the mean is, the expected value. It's going to take longer to figure out what the variance is. If you have a binomial, you've got a really simple way to come up with those answers. N times p for the mean, n times p times 1 minus p for the variance. Take the square root of the variance, you've got standard deviation. So it becomes very important that you're able to recognize when you're allowed to use the binomial formula. So you need to check out those characteristics, those 4 characteristics that you need for a binomial problem. Now the next presentation, we're going to be looking at continuous probability distributions. Specifically, we're going to be looking at the normal. So we'll talk more later.